Let's now go to our second Innovation Fund new project, and I'm going to turn it over to Andrew Peel from Peel Passive House Consulting. Over to you, Andrew.
Great, thanks, Alex. Yeah, next slide, please. Yeah, so I'm actually going to be speaking about a HVAC and domestic hot water solution that we are have developed and are implementing for passive house and net zero ready buildings. Next slide, please. Just a bit of background briefly on our company. We're a company basically dedicated to helping the industry implement the passive house building standard. Don't have any time to go into that, but I'm sure numerous people on the call have or in the session have heard of the passive house standard. So yeah, we're supporting in a consulting certification, working with manufacturers, doing training and so on. Next slide, please. So what we're finding, basically there's a barrier we're trying to address with what I'm calling the conventional high performance approach. So if you're building a much better building, so really investing in the building envelope, um, then we have an opportunity to, we're basically going to be reducing the heating and cooling loads in these buildings, and we have a potential for simplifying the system. All right, and this is actually kind of a promise of early days of application of passive house. Invest in the envelope, simplify the mechanicals. And we haven't actually quite realized that. And what we're finding is we're relying essentially on three systems, and the systems aren't really right sized for these the loads that we see in passive house buildings. So if we look at a typical multifamily scenario, we're going to have a separate ventilation system that provides our indoor air quality. We typically would have, if we're fully electrifying the building, we would have an air-to-air heat pump. Maybe the odd project does geothermal, so ground to air heat pump. And then we'd have a separate heat pump for domestic hot water. So we have three separate systems to meet the needs of our building. And so yeah, we in the end we don't really see any capital cost savings. Next slide, please. So what we're actually proposing to do is implement a strategy called supercooling or cold air distribution, which is actually an industry term they use. This is actually a strategy that's been or technology that's been implemented in commercial and industrial buildings. And essentially what they do is the air we're supplying into the building, we're supercooling that air. So instead of a regular temperature you might get off of an air conditioner, a heat pump, chiller, whatever it is, we're actually going to be dropping that temperature of the air much lower than conventional. And this is, as I mentioned, a strategy. It's been done in commercial industrial. ASHRAE even has a design guide published in the 1990s. And actually, even according to ASHRAE, this type of strategy can reduce mechanical costs and energy consumption as well. Next slide, please. So essentially what we're trying to do is simplify our system, say, okay, let's not have these three separate systems, all right? We're going to look at, okay, we're going to have a ventilation system we need for good indoor air quality, right? And if we bring the loads down low enough, the heating and cooling loads, well, that just means we need less air to actually offset our loads or our gains. And if we can either heat that ventilation air or supercool that ventilation air, then in principle, we could actually deliver all of our heating and cooling through our ventilation system. So we don't need a separate heat pump system like you have like indoor heat pump units, essentially. Right. Now we still need a source of generation for heating and cooling. So we would have a central air to water heat pump. So that is going to generate all of our heating and cooling, and that is going to be delivered through our ventilation of fresh air. And since we are having a air to water heat pump, we can at the same time do domestic hot water. So if we can advance just one, there's one more. There we go. Yeah. So we basically have these three services covered through this one heat pump, and we're delivering all that heating and cooling through our ventilation system. Next, please. So cold air distribution, as I mentioned, done already, but it's actually not been done in residential. And this is because there are three key risks to this strategy in residential. Because essentially we're targeting, I mentioned, a really low temperature. This is about 5 degrees C. And when we deliver at such a cold temperature, this is basically like opening your refrigerator, right? That's the temperature of the air we're dealing with. With such cold air, well, we could have occupant discomfort, right? Dumping air potentially onto occupants, causing drafts. We could have condensation, everyone's pulled out a can of soda from the fridge and watched the condensation form in the summer on it, even in the winter sometimes. So we want to be able to avoid that, deliver the air without causing condensation. And actually, the surfaces around the diffuser, our supply diffuser, with such cold air could end up becoming cold enough that they could promote the growth of mold. Next slide, please. So in order to address those risks, those three key risks, first phase of our project was actually to do some laboratory testing. So we rented some space at a rooftop lab they have at the University of Toronto and basically set about testing different parameters to see could we address those three risks adequately. We again don't have time to go into that aspect of the project. If we go to the next slide, though, I can briefly summarize that those three issues we adequately addressed. So through the testing we did in the laboratory, we're confident that we could implement this strategy and mitigate those risks. I have a whole other presentation on the very first phase of this project with that lab work we did. There's actually a link there. You can also search for, passive house cold air distribution. That'll probably get you the presentation. So if you're really interested in that first phase, there's more information you can find there. Next. Okay, so given the great results we got from the laboratory work, we decided let's move to the next phase and actually implement this project. And so we've actually found 7 buildings, small multifamily buildings across the country, literally coast to coast from Victoria all the way to Margaree, Nova Scotia, different climate zones. We've got one here, one in Edmonton as well. It's a very cold environment. Market rental, affordable. There's even one small condo project, mostly new build, but there's also a retrofit that we're going to test this out in as well. So really, if we can successfully demonstrate this in these 7 projects, we feel we've developed a universal solution for much of Canada. Next. So the goals of our implementation phase of the project are really to prove that it performs, so that it actually achieves its energy performance targets, carbon reduction targets, that it's actually accepted by the occupants, and that we can actually reduce operating and maintenance costs. We want to prove out that it's economical, right? So we can both reduce the initial mechanical capital costs as well as ongoing operating costs, and that it scales. And so we're working with commercially available equipment, just basically putting the pieces together in a different way and operating it in a different way. But everything is commercially available. And as I mentioned, we're testing it out different climates, different client types as well, the building sizes and tenancy types to really show the it's applicable in many different situations. Next. Okay, I mentioned we want to ensure it works for the occupants. So we're going to have a 2-year monitoring or post of occupancy evaluation campaign. So that's going to have an occupant assessment and engagement program to really get ongoing feedback from them. Are there any issues they have? How are they experiencing the system? We're going to do technical monitoring as well, all sorts of heat meters, air sensors, really getting good quality data so we can demonstrate the performance as well as troubleshoot and learn how to optimize the operation of the design and feed that back into future implementation. To support scaling, we're developing a design and implementation guide for both designers and contractors, and we're partnering with an organization I'll mention shortly for that. And we want to develop a community of practice for building managers. So the building managers that are actually working with our system across these sites and beyond in the future, that they'll be connected and be able to communicate and share their experience operating the systems. And then we're also developing a training course to help support implementation of this solution as well. Next. And just, yeah, want to mention we are working with some great organizations. We've got our build partners that are, taking on the risk of this initial implementation of our solution, both private and nonprofit organizations. We've got an education partner in AHRI. I think this might be the largest mechanical trade organization. So we're working with them on the design and implementation guide as well as the training course. We've got a monitoring partner with Enbridge here in Ontario. We've been working closely with manufacturers. We've got organizations we're collaborating with, including SRIA for dissemination of the results and the knowledge transfer products, and other housing provider collaborators, I call them, folks who are interested in our solution, not quite ready to commit yet. They want to see some of that initial data, but when we can prove out the solution, they've got a pipeline of projects that they could implement our solution in.